So now, if I take the dot product of T dot dA is gonna be is write the elements for T in terms of T11, T12, T13, T21, or rather in terms of X and Y. If I do that, this is going to be XX, XY, XZ, YX, YY, YZ, and ZX, TZY, and TZZ. So if I write the tensor elements, that includes, after you added the after you subtracted this one from this, you can come up with this element, all right? So if I write like that and multiply by the components of the area is just a three-dimensional vector, and you can express it using a column matrix, right? So in terms of these elements, I can write here dA, X, dA, Y, dA, Z, right? So, what is going to be then T dot dAx component? T dot dA x component. How can I express that? I just have to multiply this with that. That will give me the x component. So that's going to be Txx dAx plus Txy dAy plus Txz dAz. All right? So this is what we need to carry out the integration for. And so what's going to be Txx first? Txx is according to the relation that I gave you there, or just by looking at the matrix here, how can I express Txx? It's going to be this minus that, right? So that's going to be without the unit vector x, because I'm just considering here, I've already taken the effect of the unit vectors dotted with the unit vector for the area. So what you would have here is epsilon naught E x dx minus of half E squared. All right? And similarly, Txy is going to be epsilon naught into Exy minus 1, 0, right? So that's going to be just Ex dy, and Txz, what again? That's also epsilon naught Ex EXED. All right? Now, let's think of the integration resulting for these two terms. So this, eventually you are going to integrate it over theta. So if I write it here, so this is going to be a double integral from 0 to pi for theta, and from 0 to 2 pi for phi, right? You agree? So if that's confusing, let me write it here.
Dr. Enzo,
Yes.
if we did theta and 2 pi, wouldn't that be the whole sphere? We just want the hemisphere, right?
Yeah. Sorry. Theta should be from 0 to pi. Yeah. From 0 to pi over 2.
Okay.
Yeah. Sorry. Good observation. Okay. So and you can probably, if we apply that one in here, we can see something even without integrating. Okay, no, we cannot apply for theta. That's for the plane surface. For the plane surface here, what's going to be theta? If that's the next step that we are going to do, when I'm going to evaluate over this surface, I can set theta equals to pi over 2. So that would simplify things. But for that one, we cannot set. But most of the integrals, they are going to bunch. Because if I consider the integration from 0 to pi over 2 for theta, and from 0 to 2 pi of t dot dA x, so that's going to be the integral from 0 to pi over 2, from 0 to 2 pi, and dxx is going to do that. So for now, I will just write dxx. And dax is going to be what? That's going to be this, right? That's my dax. So that would give you r squared sine of theta, d theta, d phi, plus the integral from 0 to pi over 2, from 0 to 2 pi. And this one, if I write dxy, that's going to be dxy times what? dy, right? So dy is this. So I have r squared sine of theta, sine of phi, d theta dphi, plus the integral from 0 to pi over 2, from 0 to 2 pi of txz of r squared, and z component is this one. So you have r squared sine of theta cosine of theta d theta d phi.
Dr.
Yes.
Just to make sure I'm following properly, this is just the integration over the hemispherical, the outside.
Yes. Yeah, we haven't closed it yet.
Okay.
Yeah, we are considering only on the upper surface now.
Okay.
The next step is on the plane surface. Okay. So now just look at the expression that we have in here. Huh? Okay, let me check the D. Did we mess the D? Huh? I don't think it's.